the last example we're going to look at is the field from an infinitely long wire. And one thing I'll say is it doesn't truly have to be infinite. It could just be really, really long, as long as it approximates to be infinitely long. So we're going to look at this and see that this has a cylindrical symmetry in our charge distribution, i.e. there's a translational symmetry and there's a rotational symmetry along one axis. That means that our electric field is also going to have a cylindrical symmetry, and so we want to choose a Gaussian surface of a cylinder. And perhaps obviously, we want the center of our Gaussian cylinder, the axis, to align with the axis of our infinitely long wire. Now, here's something new that we didn't need to worry about with the spheres, is that only part of the length is enclosed. Now, how much length we enclose is completely arbitrary. We're going to call that L. Now, does it seem like the electric field should end up depending on how much length we happen to enclose when we calculate this? No, it doesn't really make sense. So we are introducing the parameter L to talk about how much charge is enclosed, and it will also factor into thinking about the size of our Gaussian cylinder, but you expect the electric field to not depend on L. So that's something to keep in mind. Sometimes we are introducing parameters into Gauss's law calculations that you expect to not appear in your final answer. So that's good to check. Now the next thing that's also different from when we did the spherical calculations is that we now have three pieces. We have one end, we have two ends, and then we have kind of this curvy bit in the middle. So we now have three different surfaces to worry about. So again, we have to overall have a charged surface, a closed surface, but individually it's made up of pieces. And what's going on with those pieces then is that on this end surface, everywhere your electric field, because we assume that we're going to have that cylindrical geometry and the electric field is always going to point away from the wire, notice that it's perpendicular to dA. So that's saying it's parallel to the surface. Here, our electric field is perpendicular to the surface. Okay, and then this end and this end are kind of the same in a way. So this tells us that, again, we get to do that simplification because the orientation of the electric field really is going to simplify, and so we don't have to do some sort of difficult surface integral. So, starting point, again, write this equation down. And as always, we aren't actually interested in what's happening on the right. We're really just interested now in the charge enclosed and then thinking about the electric fields and our pieces of our surface. So the amount of charge enclosed is lambda, where lambda is going to be your charge per length. Now, it's an infinite wire, so you assume it's infinite charge, but there's still a certain amount of charge per length. And so again, the total amount of charge that happens to be enclosed in our cylinder depends on the length of the cylinder. And because that shouldn't impact what the electric field strength looks like, we hope that that will cancel somewhere. Now what we think about is that our flux is going to be equal to these three pieces. So again, you have two ends and then you have that curved side. So because your ends have that angle here, right, that the electric field is actually parallel to the surface, here we get to say that, oh, those are going to be zero. That's nice. And so then we really only have one flux to worry about. And that simplifies because everywhere you have that constant electric field that is going to be perpendicular to our surface or parallel to dA. And so we get to multiply, right? We get to do that multiplying thing we like to do. And so the charge enclosed gives us lambda L. So now we have to figure out what the area of the side is. So now this is where you again have to think carefully about what you're doing. It's not the total surface area of the entire cylinder because we're not interested in the ends at this point. A cylinder here is only talking about the curvy bit. It's not talking about the ends. And so when you then go to calculate that, be careful, don't add in additional area. And so how to think about this, if you can't just remember what the equation is, right? Think about it as unrolling the cylinder. And if we unroll it, you get a rectangle. This side of the rectangle would be your circumference, 2 pi r, and then that would just be multiplied by this, which is length. So that's one way to think through that if you don't happen to remember. And so we're going to plug that in for this and rearrange to get the electric field. So I've just pulled that over to the bottom. So notice now that it is going to simplify a little bit. And that's good. That's what we want. We want those L's to cancel because we didn't expect L, which feels completely arbitrary, to matter. Now notice that R, which is the other parameter of our cylindrical Gaussian surface, that does appear, but that's okay because we expect the electric field strength to vary as a function of radius. So that's fine. This says that as you get farther away from your infinite line of charge, you in fact get a weaker field. We expect that. So if you wanted to write out the full thing, and you can group together these constants in different ways, 2 pi epsilon naught, lambda over r. Again, this would be in the r hat direction because it's pointing away from the wire. So now one thing that gets a little confusing is this isn't r hat in a spherical coordinate system, it's r hat in a cylindrical coordinate system. So I would still write it this way, but the book, for instance, might say away from wire. Okay, so you know that it's pointing out radially in a polar coordinate system, but not in a spherical coordinate system. So this is a helpful thing. Anytime you have an infinite object, you can't actually hold infinite charge. Always make sure you have a finite Gaussian surface. So hope this makes sense. Again, these 3 examples were really meant to show you the power of Gauss's law. You should be ready to apply it to similar but different situations.